phase-wise PhD students have joined. Now almost all the PhD students are there. Some masters, second year master students are also there, but no undergraduate students.
Oh, that means the research scholars are coming into the premises.
Around 70-80 have come.
Okay. Good to see you again at the GIT University through virtual mode. Because some days back, during my last conference and one seminar, and times I am disturbing from this side.
अरे disturbance क्या है? If it this topic is a different hatke.
No. Actually, he has chosen a very good topic, AI and ML, with in related to manufacturing. So because nowadays,
I am not a manufacturing man ना, but जब बोले तो manufacturing का एक problem आज discuss करेंगे. So manufacturing problem from a theoretical computer scientist's perspective.
No, with that expectation only, he requested you to just share your best experience with the research scholars and participants.
It's a faculty of, I think, na?
Yeah, all are AICTE Institute faculty members only, because since it is the AICTE approved programs. And already you have received a mail from the Raghavendra also, regarding that Atal FDP also. That will be during February 2021.
Atal FDP भी आपको मिला है? सही है.
Already ये राघवेंद्र आपको मेल किया है ना?
और अटल का? ना, I don't think. मिस हो गया होगा तब.
No. Perhaps you received one, but
Atal actually we have also got 3 in our department.
सर NIT कहाँ राजा भोज कहाँ गंगूतेली, आप भी ना ऐसे बोल के.
इस बार अटल तीन अप्लाई किए थे डिपार्टमेंट से, तीनों को मिला है. वही बोल रहा हूँ, राजा भोज गंगूतेली कहाँ से आ रहा है?
NIT अप्लाई करेगा, NIT लिखा है, मतलब चाहे NIT की जगह पे नेशनल इंस्टीट्यूट की जगह पे अगर नालंदा इंस्टीट्यूट भी होने से NIT लिखा है, उनमें से वो लोग दे देंगे.
हाँ, ठीक है, थैंक यू. मतलब indirectly you are saying that you please shut up. ठीक है, shut up.
No, not like that. Sorry, extremely sorry for it. If you have taken wrong.
अरे सर, ऐसे मजाक करो. आप भी मेरा टांग खींच रहा है, मैं भी आपका टांग खींच रहा हूँ. Okay.
और बेटी कैसी है?
All okay, sir.
All is fine. अभी आपको डिस्टर्ब करने वाली नहीं है तो?
That's why I came to my office.
Oh, you're too clever.
Otherwise, when I take classes, sometimes she comes for a minute or two. It's a welcome break for students and for me. But, this is not the proper place. Classes, we have 3-4 classes every week.
Yes.
That is permissible. इसमें थोड़ा सा ठीक नहीं रहेगा.
प्रोटोकॉल तो फॉलो करना है.
I also had some work ऑफिस में, कुछ पेपर्स जमा करना था ऑफिशियल, वो सब भी कर देंगे. But we have a meeting at 12 o'clock, directors meeting. Sari is conducting a faculty meeting after almost 6-7 months after this corona time. Wednesday usually first up we don't have classes. So
right now your colleague is heading the department, no?
I am not the HOD now.
No, right now you are not.
My tenure is over. Senapati, na?
His good name?
Madam was there. Madam is on maternity leave. So another madam is there now.
And your rotation will be again after 3 years.
Once everybody else gets a chance then. So that means not in my lifetime.
Oh, not in your...
The first tenure you can't deny. You can't say no. Second time I'm sure they will give us an option. Sir, why are you recording this part of this? We have not started.
No. Oh, actually,
not started. Sir, no. Now it.
Kali sir, apna ida pore remove kar debe. Just pothe lago bola.
Sir. Now started might be. They started now at 10.
Sir, your participants are already there with you.
Yes.
Over to you and Kali sir.
Okay, great.
I'm in off mode.
Okay. So I'm beginning then, sir. Okay.
Sir, 1 minute. Roger sir.
Kali sir,
Broji sir, just tell to Paresh to stop this one and again restart the new recording.
हाँ, that will be.
ଆପଣ
Because I am attached with the mobile, through the mobile here.
नो प्रॉब्लम ଆପଣ ଲାଗି କଲ୍ ରିମୁଭ୍ କରିବାକୁ ଏଡିଟ୍ କରିବାକୁ କିଛି ଅସୁବିଧା ନାହିଁ ଡୋଣ୍ଟ ୱରି
Okay. No problem. We will see it.
over to you Kali sir and start
Sir, thank you. Thank you for the nice, you can say the
Dipton
interaction.
sir हम लोग बाद में बात करते हैं थैंक यू सर
Sure, I'll catch up with you later.
या थैंक यू
So good morning to all. It's my privilege that to welcome Dr. Diptendu Sinha Roy sir from NIT Meghalaya. Actually, sir, we from the AIT University and from the Department of Mechanical Engineering, we heartily welcome to you to this AICTE sponsored FDP program. Actually, what I will tell you about you, sir, you have done and you have exposed such a nice research field on your arena, and you are guided and you are smoothly handling the R&D work very nicely. So with the short biodata, I will just let introduce Dr. Diptendu sir. Sir's interest is in the grid, cloud and distributed system, data analytic and smart grid domain, application of soft and evolutionary computing, software reliability, and sir is working with the IoT, have the vast knowledge on that one. And he have written book chapters, and he have a huge number of international publication in the standard or reputed journals. He attended the national and international conferences and published so many papers there in from this his research area. And he also guided 4 PhDs and some ongoing also. And so many bucket of MTech programs students also get guided by him. And he conducted national international conferences and also attended so many national international workshops, seminars and conferences. Right, he has a membership, professional membership of IEEE, Computer Society of India, IST, UACE, etc. And he also awarded with a paper present award at the international conference for the year 2014-15 awarded by Computer Society of India Region 4, awarded at 15th CSA annual convention held at New Delhi in December 2015. They have a, you can say that the biodata of such persons, we can say that it's a very big, and with this one we get pleasure, and particularly I am taking the pleasure. Diptendu sir, be connect with you, and very nicely you accept, and our you can send that request, and from your busy schedule you have given some times to us. For that reason, we will thankful to you. So welcome Dr. Diptendu Sinha sir for this program. And I, on behalf of the participant also, I welcome to you for this program to share your experience and guide something for the research activities. Thank you, sir. Now I handed over this one session to the Diptendu sir to continue the session.
Thank you, Professor Ratho, for the kind introduction. So right
Am I
at the
audible, sir?
beginning, am I audible, sir?
yes sir
Okay, great. So thank you very much, Professor Ratho, for the kind introduction. It's always a pleasure to support old friends and friends. So it's my duty also. I'm duty bound to do that. However, to all the participants, let me give a statutory warning before I start. The warning is that I am not a production manufacturing person. However, I have, as a part, as Professor Ratho told, I have done a lot of work from different application domains using machine learning, data analytics, and soft computing, evolution. So today I would rather share, because fortunately I saw that one of the works which I had taken up in 2016-17 for one of my PhD scholars. So he's a maths person. So he has done his PhD from Shastra University, Dr. Rao, Madhusudan Rao. So as a supervisor for his work, actually, I got to know about, I mean, his thesis was on hybrid evolutionary computing solutions for different existing engineering problems, some medical problems too. So as a part of it, fortunately, unfortunately, I came across this problem called the cell manufacturing problem. So the statutory warning is that I'm not a manufacturing production engineering person. So probably this session would give you an exposure to this problem from a computer engineers, mathematicians perspective. So some relevant application side details I might miss. So I would apologize rather at the beginning than at the end. But still, I'd be happy to share my experience with all of you about what work we can do, how we can extend these works, right? So I think that's good. So I will just share my screen before I move ahead. Yeah, I hope my screen is visible to all of you. I'll share my material. Yeah. So I'm Dr. DSY. I'm an associate professor and of the computer science department at NIT Meghalaya. So in case you have any queries, you are free to contact me over this email. I'll start this problem. So basically, the cell manufacturing, cell formation problem. Just a moment. I think it's better that I will switch off my video because that might interfere with the bandwidth a bit.
Yes, sir. Yes, sir.
That would be better. Better not to take a chance with. Yeah. Hide this. Yes. Good enough. Okay. Yeah. So let me stop a bit here. Basically, as you can see, the title of one of the works which I had done, as I told you 3-4 years back, was designing of certain hybrid meta-heuristic algorithms. So basically, evolutionary algorithms. We used a very specific evolutionary algorithm. We call it the clonal selection algorithm. However, I will, in the first part, as you can see, there is one more part to it. The problem is from a cell formation problem, which is actually a production engineering manufacturing problem, okay, from the manufacturing industry. So what it is, the manufacturing technology, as we all know. So here, there has been a lot of applications of group technology. Okay, so if we can, I'm just giving you, despite being not a man from manufacturing and production engineering school, just to give you an overview, maybe 5 minutes I'll spend on this problem and how the different approaches have moved to what modern day manufacturing, where modern day manufacturing stands. Okay, so whenever we think of large scale industries, particularly in the production and manufacturing domain, so traditionally we had, the industry had moved for efficiency purposes and moved for assembly line sort of arrangements. Okay, so that the overall turnaround time for different manufactured objects can be automated and be made very efficient. Okay, however, as the industry moved on, so assembly lines, they work very efficiently as long as the product is a single product. In a manufacturing plant or a manufacturing unit, a single product is being manufactured. However, where the manufacturing can be done, big large scale industries, manufacturing industries, they thrive on manufacturing different products, so at the same time. So this brought into the problem mix a new dimension. This added a new dimension, the dimension of adaptability, where different products could be manufactured by the same unit of the machines, let us say, and the parts which were involved in producing those products, and then the system, the manufacturing, the components, the machines could organize themselves in such a way that they could take care of the differences in the products, being different products which comes as output. Okay, so as usual, as a very intuitive problem, group theory was being applied. So the idea was how to group the different parts and the different machines within the manufacturing plant, such that the overall efficiency of the machines being used to produce the throughput of the parts which are being developed, so they can be maximized. Okay, so different group technologies problems were discussed. It's a long history. It's not about just 1 decade or 2 decades. From the 60s, 70s, 80s, there have been revolutions. Okay. So we'll not go into the details, and neither I have seen this industry very closely, but this is what I get to know. Okay, so many combinatorial optimization techniques have been applied at different parts of the entire production system. They are there. However, I will take a very mathematical, a mathematics perspective to explain to you, and then we'll move forward. Okay. Okay. So, as you can see, from the slides, that and the discussion which preceded, that the long-term productivity of a manufacturing unit, so that significantly decides the outcome or the efficiency of the entire plant. So it depends on the underlying design optimization, the strategies which are involved. Okay, so however, one of the fundamental challenges which are associated with the production environment is the minimization of production cost while not compromising on the production quality, obviously. So many popular techniques have been used over the past decades to accomplish these goals. However, for any manufacturing process, one thing that remains common is that there are different machines which are employed to move the different parts from one place to the other. Hence, such movements give rise to additional costs, not just the cost in terms of the money which is incurred, but also in terms of the time it consumes. So efficient manufacturing, if we can't if it is not just cost efficient, if it is not time efficient, that also leads to lower utilization of the entire production system, which essentially again means rise in the cost, additional cost. Also, at the same time, there are frequent variations in the production orders. Okay, so you can see it in small scale industries, we can see it in medium scale industries. So this leads to a situation where the setup for producing different production orders, so the setup time actually consumes a lot of time. Okay, so naturally this reduces the overall productivity of the production system. Okay, so for this
Hello, sir. Hello, sir. Sir.
No voice is coming, sir.
Yes, sir. No voice, sir.
There's no audio.
Hello, Raj, sir.
Shravan sir, little bit network issue might have.
Oh, okay,
From
okay,
the
okay.
Not,
Okay,
not
okay.
from
No.
the BSNL bandwidth,
Oh.
BSNL bandwidth and the Airtel bandwidth both have a loss, all of a sudden low down bandwidth.
I think my side is there. I think, sir. So only.
No.
Okay.
No. Shravan sir. Shravan sir.
Yes, sir. Yes, sir.
During the program, audio is clear, na?
During the program, his audio is clear, sir. But today
PPT,
only.
etc.
Yes, sir. PPT, all thing, everything okay. But today only, I think. Yesterday also in afternoon session, some bleaching is there.
Yes, sir. That is the central bandwidth problem from the
But
Airtel and BSNL.
the program is going well, sir.
And we have a connection for Airtel and BSNL only.
Yes, sir. Yes, sir.
Okay,
No problem.
we were trying, sir. Again, I want to contact with sir.
Okay.
Sorry to say that due to the certain network issue problems, we are not able to contact with the speaker also. So, I have a presence. We will trying to reconnect to everybody.
So sorry. I actually I muted my phone, so I never saw that some phone is coming. Okay. Okay. I'll continue, sir. Yeah, thank you. Hopefully, I'm audible now this time. I kept on speaking, I never realized. Okay, so I don't know where I stopped, so better is that we start from the beginning. In the chat box. Okay, great. I'm audible. So I think do I need to share my screen once again? Okay. Okay, so if it is 5 minutes back, then I'm sure that I have not covered what I wanted to cover till now. But in the meantime, I had already gone to actually slide number 5. So I'm not sure how far it was audible to all. So let me do one thing. I'll very quickly summarize the entire process once again. So any production system, I mean, okay, maybe from here only I will just summarize, even if I have explained it previously, but still you please bear with me for the repetition. So the this presentation will basically tell that entire thing can be divided into 2 parts. First is this cell formation problem. Okay, so cell formation problem, and the second part is the meta heuristic solution for that. Okay, the evolutionary computing solution to that. So briefly, what is the cell formation problem? So this I discussed, that the productivity of a manufacturing unit, it significantly depends on the underlying design optimization strategy. Okay, so one of the fundamental challenges which is associated with such a production environment is the minimization of production cost. But not to forget that this production cost minimization should not be at the cost of compromising the product quality per se. Okay, so many popular techniques has been studied, group technologies, as we will see. One of the fundamental techniques which was used for production, in making production systems efficient, was the assembly line system. However, those were suitable only for as long as the products did not change. So for static products, worked good. However, when the same production environment was envisioned to be used for producing different types of orders or different types of products, in such cases, group technology was envisioned to be a very efficient solution. Group technologies, where the different machines which are there in the production environment, they were being grouped to be used by for producing different parts of the within the orders, and the flow of this production system was orchestrated in a very in an optimal way, so that the overall efficiency of the system, production system, increases. Right. So very briefly, I'm summarizing this. So group technology is again a mathematical concept which has been studied from as late as 1960s. Okay, late 1950s, early 1960s. But the application of group technology to production environments, okay, so they started quite late. This cell manufacturing problem. So this reference, I'll give you the paper where I'm talking of, where these references are there. So that I'll share in the chat box at the end of the lecture. Okay, so they started in 2006. Okay, so what does group technology do? So it identifies and creates the manufacturing cells, which essentially means, we have a set of machines in your manufacturing system. So to divide those machines into different cells so that the different parts can be efficiently produced. Okay, so group technology identifies and creates the manufacturing cells in which a group of machines can operate a product family with little or practically no intercell movements. So what is intercell movement? So see, as we have talked that there can be different products over a period of time. So as long as you are producing the same product, you can optimize it using, as I told you, assembly lines and so forth. So there is the same process is orchestrated again and again to produce different. So there is no movements per se. But when a new product comes in, the optimization, the strategy to control the different machine, the flow of the machine parts from one machine to the other. So this has to be redefined to improve or increase the efficiency of the different machines. So, or rather the utilization of machines, because if all the machines are utilized better, then overall production will naturally be more, productivity will increase. Okay, so however, if machines at runtime, when the production during production runtime, if machines are waiting for the different parts, okay, so the parts come in and come out, so these movements cause a lot of delay. Okay, so they reduce drastically the efficiency. Okay, so before we go into that, I mean, there have been different categories of studies, solutions for the cell formation problem per se. So there have been similarity based techniques, clustering techniques, evaluation algorithms, ANNs have been used, and more recently these all these solutions were targeting one objective or the other. Okay, later on we'll see what are the objectives that we have studied in our paper. So in recently, with the abundant availability of computational techniques, we have also been trying to optimize the same problem, addressing multiple objectives. Okay, we'll see later on. We start off with a very simple example. The basic, let us go through the basic cell formation problem first. Okay, so the cell formation problem can be represented as a binary incidence matrix. So where its rows represents the machines. So here it shows the machines. So these are the machine numbers 1 to 5, and the different parts which are being corroborated are represented. This shows a 5x5 incidence matrix, and this is a binary incidence matrix. So basically entries will be 0 or 1, and entry here 1 means that part 1 would require its service from machine 1. It would also require its service from machine 3 and machine 5. On the other hand, that entry here 0 means that part 1 does not need any support from either machine 2 or machine 4, which is not the case for machine 2. Machine 2 doesn't require part 2. Part 2 doesn't require machine 1 or 3 or 5. Rather, it requires machine 2 and machine 4. And similarly, there are other parts also. So if you have a closer observation, you can see that just so that we can save some time later on. So part 1 requires machine 1, machine 3 and machine 5. Same is the case for part 3. It requires machine 1, machine 3 and machine 5. So you can think of it. Same is the case for, and similarly there is one more group which is which you can see. Part 2 requires machine 2 and 4 only. Same is the case for part 4 and part 5. So now, based on the previous discussion, it is obvious that we would like to group these different parts and assign them to different machine cells. So from this set of 5 machines, if possible, so if possible is a big statement. If possible, we would rather like to divide these machines into smaller cells, number of subcells, and assign this group of parts based on intelligently on 2 different groups, such that certain objectives are fulfilled. One of the objectives from the previous discussion is that we don't want inter-cell movements. So when we group these machines into different groups, we call them cells, into different cells. So we would rather want that there no inter-cell movements are there. So parts don't move from one cell or one subset of machines to another cell, another subset of machines. So that would require at runtime the production environment to be stalled for a certain amount of time. So again, this can also be thought of as a sort of setup problem. Okay, so in this said incidence matrix, any value at a location ij, so depicts the involvement of the ith machine and the jth part. Taking class. Sorry. So similarly, the value of 0, as I already told, at any position, say per se m comma n. So this indicates that the mth machine is not involved in the production of the mth part. So for example, you can see it from this example 1 and this part, this A part. Okay. However, based on the definition of how we define cells, which are basically some subset of some way of grouping the cells into a subset of these 5 machines. So if we rearrange it, so for this one example, this figure B figure, so it says, it reads as the optimal block diagonal matrix for 1A. 1A is this particular figure, right? So after an appropriate rearrangement of the top matrix, so the bottom matrix, which is marked as figure B, so this can be obtained. So it can be observed that in case of 1B, that there are no ones in the non-diagonal block. So this block, so based on this observation, which I'll try, hopefully this time the pointer works properly, otherwise here what we observed that, okay, we observed that part 1, part 3, part 5, they have a similar grouping property in that they use the machines 1, see, machine 1, part 3 also uses machine 1, not 5, sorry, not 5, 1 and 3, 1 and 3, only 1 and 3. So they require machine 1, machine 3 and machine 5. So based on this observation, if we can group this particular matrix, rearrange it into such a block. What block? Okay, so here you see in this way we are rearranging it, the same matrix, and we get 2 blocks. Okay, so what we have, 2 and 4. 2 and 4 have similar properties. They use machine 2 and machine 2. Both of them use machine 4. None of them use machine 5 or machine 3 or machine 1 per se. Okay, so we put them together, right? So similarly, what about machine part 1 and 3? So they have been relegated to the other side. We have just rearranged this to get the block diagonal matrix. From this matrix, we have transformed it, moved it. The rows and columns have been just exchanged. Their usages, so that the usage of those parts, which part requires which machine, that dependency is not altered after the movement. Okay, so what we have done in this way, you can find that we have grouped it into like diagonal matrices. Okay, so this goal, in short, I'm saying, the goal here is to divide the entire production system, rearrange it in such a way that we divide it into this matrices into block diagonals, right? Block diagonals, and the goal here is to keep in the diagonal elements, to keep as many ones as possible. So what is the goal of such rearrangement? There has to be a goal. The goal is that the ones in diagonal matrices and zeros in the off diagonal matrices. I'm not sure whether am I still audible? Hope I have not got disconnected. I can see myself.
Yes, sir. Yes,
Great. So here, therefore, it can be said that for this particular figure, let us say this is 1B here, example 1 and B. So in this figure 1B, which is this can be we call it the best cell formation solution for the problem which has been shown in figure 1A. The rearrangement involved in the grouping of machines and parts is as follows. Like we divided into 2 cells. One cell comprised of the machines 2 and 4. Machines 2 and 4 here. Here, machine 2 and machine 4. The other cell comprised of machines 1, 3 and 5, and also the parts. So parts were also divided into two groups, part 1 and part 2. Part 1, let us say, comprised of parts 5, 2, and 4, and part 2 comprised of machine cells 1 and 3. So now the mapping between these machine cells, these two machine cells, and is comprising of a subset of machines. So what are they? In this case, C1 and C2 involved. So the entire group is, let us say, C1, C2. So what is C1? C1 comprises of two cells. So what are the machines involved? 2 and 4 in, say, cell 1, and the remaining machines 1, 3, and 5. I have already discussed their respective dependencies from the observation. What are the parts? We also divide the parts into two subparts, two groups. They are the first group, let us say 5, 2, and 4, again based on their similarity or dissimilarity of using the different machines, and 1, 3. Okay, so the mapping, so you can say that this is C1, this is P1, this is C2, this is P2. So now our job will be to map these different parts to corresponding cells, and that would look something like this. Arrangement should look like this. C1 will be, I mean, the part P1 will be mapped to C1, and the part C2 will be mapped to P2. Okay. So this is the best solution. Why do we call it the best solution? It is called the best solution because, as you can see in the diagonal matrix, after this rearrangement, all the elements are 1. This ensures that there are no voids. Void, we will formally explain it, but then there are no unused machines. So the utilization of all the machines are ensured, and in this off diagonal block here, in this off diagonal blocks, you can find all zeros. Okay, so this also we will define later on formally. Okay, so however, I mean, this is a very specific example for which we could obtain a best solution. So we don't need any optimal solution for this, because it's possible to have a best solution, right? On the other hand, though the best solution for this particular example was solved, later in this particular slide we will see another example where after doing the grouping, it is not possible to have a best solution. Why? Because as you can see here, this shows you an instance of part 2, which doesn't use machine 4. So this is a 0. So in this block diagonal matrix, this is the diagonal matrix. So in this matrix, it would have been. So we find that machine 4 is underutilized. Okay. So similarly, in the off diagonal matrix, we find a few ones. So these ones mean that there will be some inter-cell movements. So because this cell was not supposed to use these parts were not supposed to use this particular cell. They were used to this cell 2 and 5. So as you can see, it is. I hope this is color is visible. So this has been grouped. So for this particular problem, machines 2 and 5 have been grouped to form a cell. So parts which are being produced by cell 1 now uses cell 2, which was not the case in the previous example. So parts which were assigned to cell 1, so now they were not using cell 2 at all. But this is not the case. So we should not conclude that in all possible cases we can ensure. So this would mean that there would be inter-cell movement. So the parts which were being produced by this cell, let us call it cell 1, this machine 2 and 5 together. So now they will also use machine 1 and machine 4, which is in cell 2. Okay, so this would lead those parts to be moved from cell 1 to cell 2 during the runtime of the production process. Okay, this would make it sufficiently slow. same is the case. So what we can observe, so you can observe that it is possible that even after rearrangement, some zeros might remain in the diagonal blocks and some ones might remain in the non-diagonal blocks. Okay. So after rearranging of this matrix, this particular matrix, which is shown in 2A, let us say. So in 2B, there are 4 ones which are present in the non-diagonal, off-diagonal matrix. Okay, 1, 2, 3, and this 4th one. Okay, so these are apparent blips. Okay, so this denotes that there is one idle machine, while one idle machine here, as I told you, machine 4, and while other machines are working, and 4 intercell movements. So the rearrangement that is involved, the rearrangement that involved the grouping of machines into parts did not lead to an ideal solution, best solution. So these non-diagonal ones, which are shown in figure 2, they are called exceptional elements. Okay, so these non-diagonal, these ones, all these ones, they are called exceptional elements. For efficiency, I mean, for making it easy, hereafter we'll write it as double E. Okay, and the zeros in the diagonal blocks are called voids. Like for this 0 here, this is called a void. So non-ideal cases. So it has to be understood that for when we design the corresponding block incidence matrix for any production system, we will try to optimally rearrange it, and after rearranging, we should not conclude that there will exist ideal solutions for all these all different test cases. It will not be. So however, there will be certain exceptional cases, exceptional elements and voids. The goal of the production system designer should be in such a way that we can reduce the number of exceptional elements and the number of voids. Okay, so exceptional elements and voids signify intercell movements of parts and machines of idle times during their manufacturing process respectively. Okay, so intercell movements and voids. So a void means a machine is being underutilized. Exceptional elements means at runtime of the production system there will be intercell movements, both of which are not welcome, not good. Okay, so the total number of exceptional elements and that of the voids in this second figure are 4 and 1 respectively, as you can see. So this would lead to 4 intercell movements. So these 4, 1, 2, 3 and 4 would lead to 4 intercell movements. Okay, for ease we would call them ICM. Just in future now, when we do, I mean, formulate our problem, we'll be using these 3 abbreviations. EE standing for the exceptional elements, ICM standing for the intercell movements, and V standing for the number of voids. So we found from here, in this case, for developing our optimization problem, so a manufacturing cell formation problem let us make it okay, MCFP. So it is desired to, for such a problem, it is desired to satisfy the following conditions. Number 1, so minimize EE. Number 2, minimize intercell movements, and number 3, we'll try to minimize the voids. So these 3 serve as the starting point where we identify our objective functions. Okay, So then we will move forward. So during solving any multi MCFP problem, manufacturing CFP problem, these three objectives should be minimized. The first objective is to minimize the number of exceptional elements, so that what effect it has, so that it can reduce the part manufacturing dependencies over the different cells. Okay, so it should be understood that a minimum number of exceptional elements do not always signify minimum part movements. So there is not a one-to-one relationship is there. It's a general overall conclusion. The second objective is to minimize the number of intercell movements of a part to reduce the transportation time and production cost. Okay, the minimization of these two objectives leads to the minimization of manufacturing time of the part, but minimization of the first objective does not always minimize the objective number 2, because there may be dependencies of part manufacturing, and also there might be dissimilarity among the different parts and their corresponding machine cells. Okay, so don't conclude that this objective 1 and objective 2, these two are not interdependent. Okay, so these two are one affects the other, so it's not like a proportional sort of you cannot apply proportional logic that if objective number 1 is affected positively, objective number 2 will also be accordingly accordingly affected. So that is why we keep, while doing our studies, we keep both exceptional elements and the intercell movements both as part of our objective functions. Okay, so we'll be using a few some parameters, so those names will take on later on. So let me write it out so that when we write the equations, it will be very obvious. I don't have those in the slides. Some basic parameters like for this formulating the problem. So what we are doing now, trying to formalize this objective function, or formalize this particular cell formation problem. So let us say M stands for the total number of machines, and N stands for the total number of parts. Okay, and and M be the number of sets of machines that we have. So we are don't confuse, from all the available machines during cell formation problem, we are trying to make sets. So in the previous examples, we had made 2 sets. Now we have divided the set of machines into 2 cells. Okay, so accordingly, similarly, P is the set of parts. Parts also we divided into 2, and then we did the assigning. Okay, and 2 more notations, M min and M max, where M min stands for the minimum number of machines. So there is a restriction on this, the minimum number of, I'm writing machines like this in each cell, and this stands for the maximum number of machines in each cell. And what does any value xij represent? So in the incidence matrix, it can either be a 0 or a 1 because it's a binary incidence matrix. So what does a 1 represent? It represents that the ith part production depends on the jth machine. And if it is not dependent, so that means part j doesn't need machine I at all. Okay, so from this, these are the basic parameters, and however, we have to observe this thing. The index I will be used for parts for all subsequent discussions. J will be used for machines, and the index K will be used for cells. So machines will be grouped into different cells. So for cell purposes, we'll be using A as an index. Okay, so few more let C be the set of cells. So what will be the number of cells in that C? So these notations are very important. Okay, so it will be the total number of cells. Okay, so if there are C sets of cells, so total number of cells will be within those set of cells will be mod of C. So what will CK represent? So it represents the basically the kth cell from the set of cells. Okay, and similarly mod of CK, this will represent the total number of machine as per following the same protocol here. Total number of cells, sorry, total number of machines in cell K. As I told you, K will be used for as an index for K. Okay, similarly PK will represent the kth part family. So because see, machines are divided into cells, similarly parts are divided into part families. Okay, so PK and mod of PK will represent the kth part family and the total number of parts in part family K. Okay, right. So that's it. So with this basic discussion, we now move forward. So we go into the modeling of it. So block diagonal sum. So how do we find out the block diagonal sum? The block diagonal sum can be expressed as basically Xij. What is Xij? Excuse me. Xij. So this Xij, whatever element is there, Ij already told, I is used for parts, J is used for the machines. So you have to do a summation over it, triple summation. So for all values of I belonging to the part family, then within that part family for all values of J within the kth cell, and where the K varies from 1 to the total number of cells. So we have divided the production system into a number of cells, each comprising of a set of machines. So we sum it over all such cells which are possible, and individually the parts and the respective cells. Okay, so how do we represent objective 1? Objective 1, what was it? Objective 1 was our EE. Okay, exceptional elements. So how do we define that? This will be defined as two summations. There are M machines, assuming that I equal to 1 to M, J equal to 1 to N, Xij minus this triple sum which we have defined now. Okay, K equal to 1 to total number of cells, J belongs to CK, and I belongs to PK, all the part families. So we do it for Xij. So this will give us the number of exceptional elements. Similarly, the second objective, we'll just write each of them. Objective 2, which is the intercell movements. So this can be defined as I equal to 1 to N, J equal to 1 to the total number of cells which are there, all belonging to J equal to 1 to M, and we find this Xij, Y, Jk. Okay, and objective 3, which is the number of voids, we find out as K equal to 1 to the total number of cells which are there. So in cell K into the number of parts within that cell for summed over all the cells, minus k equal to 1 to the total number of cells. This is j belongs to ck. This is I belongs to pk. Then xij. Okay, so these are the three objective functions. We have transformed. I've already explained that. Defined them with the small example which we saw how to count the number of exceptional elements. Basically, the exceptional elements, as you can see from here, the exceptional elements are the ones which remain in the off-diagonal matrices. So the total number of them. So how to find out? So we are formalizing this exception. And similarly, what are the number of voids? That is also represented by the number of zeros in the diagonal matrix. So anyway, formally, when we do the optimization, so these are their corresponding representations. Now, there are some other hard constraints which have to be remembered. Very, very intuitive, very common sense constraints. Okay, so one is that Ci and Cj, so this should be null. So there should not be any intersection. Okay, for all values of I not equal to j. Okay, so what does this constraint ensure? So this constraint ensures that each machine belongs to exactly one cell. So it's while dividing the machines into different cells, we can never what happened? Okay, we can, while dividing the machines into cells, we can never assign one machine into two different cells just to reduce the number of ones in the off-diagonal matrices. That is not allowed. Okay, so this is a hard constraint which has to be followed. So this basically says that each machine belongs to only one cell. So it cannot be shared. There cannot be any shared cells. So mutually exclusive in that sense. Another constraint pertaining to the machine, to the parts, are pi intersection pj. So that should also be null for all values of I not equal to j. So instead of here, in this each machine, it will be each part. Okay, so each part belongs to exactly or only one part family. Okay, another constraint says that once you divide the entire set of machines into a number of cells, so the union of all of them should be the entire. So that means there is no machine which is left out. Okay, and no left out, no left out, no excess. Okay, so this okay constraints. So that is similarly same is the case for the part families. So P1 union P2 union all the different machine parts which are available. So these two together, these constraints, what do they represent? They ensure that all cells are mutually exclusive. All cells and part families and all part families are mutually exclusive and exhaustive. So nothing is left out either. So no sharing of any machine or any part family among two different cells or two different part families. Similarly, no after doing this grouping, nobody is left out, neither any machine part or any particular machine. Nobody is left out. So together they mean subset exhaustive subsets of C and naturally P. Okay, similarly. So in this way, these are the hard constraints which we can find out. So now we'll go back. We're having this basic discussion. Now we'll move forward on the manufacturing cell formation problem. I think I've consumed a lot of time. Hopefully I'm still audible and visible. At least I am still in the meeting. I can see from my end. Okay. So now the question comes that how do we, once we discuss this, I'll just very briefly tell you, because going through the slides is also, let's see where it is there. It's not there. So at this point in time, one very important thing which we have to remember is that, we have to remember is that once we say that we have reorganized the different machines and their different parts into cells and part families, and then rearrange them to get the block diagonal, that incidence matrix. How do we compare? Because particularly for bigger set of machines, I mean bigger production systems with large number of machines and part families, there will be different options of doing this block diagonal matrix. You can understand, I mean the number of combinations will be very large, right? So you can think of it, if you have 10 machines and 10 part families, or 10 machines and 20 part families, so you can organize the diagonal matrices in different way. So the groups, the number of cells, that can be 2 or 4 or 5. So for 2 there can be, for 2 there will be one set of block diagonal matrix. For 3, when we group them into 3 different cells, and let us say 4 different part families, so then the arrangement will be different. So a vast number of possibilities can be there. That is why we say that this problem, this manufacturing cell formation problem, this is actually a NP-hard problem. So there are no polynomial types algorithms which can be designed for this. Okay. So however, how do we compare all these from all these different combinations which may be possible, which may be set up as different possible solutions? How do we compare them? So we use 2 different what do you call that, performance parameters. Okay, so the performance parameters, I think there's a problem only with this slide, so let me go back and write in this slide. So we identify the performance parameter. This is a standard performance parameter which has been used by practically all the different researchers who have worked on this. The previous one, they used to use group efficacy. Okay, so the group efficacy we defined as eta as a factor of q, a weighted average of q eta 1 plus 1 minus q. Q is your balancing factor, the weighted sum, eta 2, where what is eta? So that eta 1 is the ratio of number of ones in the diagonal matrix, is the ratio of number of ones in the diagonal block of a solution matrix and the total number of elements in the diagonal box. Diagonal block, right? So in a diagonal block, just let here is the diagonal block. So there are 2 cells, as you can see. So here the total diagonal blocks are 6 in this particular cell. 6 of them are ones. So it is the eta 1, the efficiency here. I don't know, writing is a problem in this particular slide. Eta 1 will be 1 here for this particular cell, because it's basically 6 by 6, the total number of blocks. So similarly, we can find it from here. For this, it will be total number of ones are 5 and the total number of elements are 6. Okay, for this cell. So like that, we can find it out. Okay. So, so this is one part performance matrix. Okay, we did not define eta 2. Okay, and eta 2 is the ratio of zeros. Eta 2 is the ratio of zeros, where naturally in the off diagonal block. I'm not writing the whole thing, in the off diagonal block of the solution matrix and the total number of elements in the off diagonal matrix. Right, the same way. So you can just find out eta 1 and eta 2 from here itself. So this is the, for this particular block, so there are total 9 elements, out of which the number of zeros are 9 minus 6. So here for this, the eta 2 for this cell will be 6 by 9. This cell. Similarly, for this cell, the number of zeros are 3 by 4. So eta 2 will be, so like this we can find it out for every block. Okay, and Q is the like weighted average, right? So later on, for comparing purposes, not just performance matrix. So this was traditionally being used. More recently, another term, related term, which is being used is the group efficacy. So literature uses both. So let us call it group efficacy, GE. I mean, we write group efficiency as eta, group efficacy as G. This is the standard way to do it. Although if you abbreviate, both stands for G. So that confusion has to be avoided. So this is represented as E minus E0 divided by E plus EV. So what is E? E represents the total number of ones. I'm not writing it. So anyway, I should write where E represents the total number of ones in total number of ones in the machine part incidence matrix, and E0 is the total number of E0, the total number of ones in the off diagonal matrix, total number of ones in the off diagonal matrix, and EV is the total number of voids, as the name suggests, total number of voids in the diagonal matrix. Right. So this is all about the cell formation problem. So ideally what we do, we have to find out, as I told you, that this problem is a NP-hard problem. So it is quite obvious that for solving these three minimization problems as together as a multi-objective problem, so that can be solved using, usually we prefer evolutionary algorithms because they are very tuned to that. We take heuristic solutions. We take, I mean, there are different evolutionary algorithms use different randomized processes to initiate, and I mean, they don't do a hard solution to it. Okay, but at the end of the day, we all ensure that all the other constraints, hard constraints, are maintained, and we get an appropriate solution. So different evolutionary algorithms has been used. So we use, as I told you, we use meta-heuristic or evolutionary algorithms for such problem, particularly because of the stochastic nature. So why do we use it? Like conceptually telling, so suppose this is your entire search space. In the entire search space, so if you do a brute force searching techniques where we start from here and then let us say search space means the solution space, so we keep on going row wise, column wise, and trying to find all the solution. It is actually with the num where the m and n, the number of machines and the number of parts, and they are very large, so it's actually prohibitively large. The exploratory space is too large to handle. So what meta-heuristic algorithms do, usually they are, most of them are like population based. So they take some random solutions within this search space, and then using some let us call it some sort of a function. We define some sort of a function which ideally suits this, I mean, for this multi-objective problem, that whatever objective function we define, so based on that we evaluate all of these solutions and we attach weights. There are different ways different evolution algorithms work. So we attach weights to each of these functions and then see what is the performance of what is the performance in terms of the objective function value for all these solutions. So better solutions are given priority, and then the solutions again in the next iteration they are modified. So modified new solution points are found. In this way, instead of searching with brute force, so they search only those localities where better solutions can be expected. So there is no theoretical guarantee that such techniques should work. However, it is observed, particularly for large-scale optimization problems, they have proved to be very, useful. Okay, so that we shall define. So in this particular work, what we did, we used one specific meta-heuristic, which we called the clonal selection algorithm, which shall use CSA for this. So we solve the MCFP problem, manufacturing cell formation problem, using the clonal selection algorithm, not the pure clonal selection algorithm. Later on, I'll just highlight, because we will not have time to go through the step-by-step mapping of this problem. Okay, but we'll provide you very basic details. Okay, so CSA clonal selection algorithm is actually a nature-inspired algorithm, which basically imitates our natural immune system. Okay, particularly for vertebrates like us. So while there are some detectors, the human immune system, or for that matter the animal immune system, they have something called detectors for detecting new pathogens like viruses and identifying new intruders in the body. So detectors are characterized by a mechanism to improve the recognition performance, and this is iteratively improved into, and this iterative process of this is known as the affinity maturation. Okay, so the fundamental step in a cell formation in a CSA, okay, in a clonal selection algorithm, is to define the structure of receptors and to represent the problem solutions. So based on the structures of receptors, a set of initial population is generated, which we call R. So the basic parameters of CSA are, one is called R. Okay, so what is R? It is a set of initial populations which are generated. So as I told you, different evolutionary algorithms use different nature-inspired features. So this CSA is inspired from the immunosystems for most animals, vertebrates. Okay, so how they work? They have something called detectors, and detectors are those cells in our immune systems which are responsible for identifying pathogens outside world, like coronaviruses and all. So they identify. Those cells are called receptors, detectors. So those detectors over a period are again iteratively made more and more active to, better suited to identify new pathogens. Okay, so we will characterize it with a small example. I think it will be there in the slides. Okay, and over a period of time, we also use AF, an affinity function. Okay, so for every problem, we have to define the problem specific affinity function. So an affinity function has to be developed to determine the strength of a solution. Okay, so in the previous example where I think somewhere I was drawing, that's such here. So here, we get a solution. We take a random initial population here. We don't do the entire brute force searching. So now for this particular population which is generated in the nearby periphery, we try to evaluate the objective functions. Same for here, same for here, same for here. And then how do we compare? Because unless we compare, we don't know which among these initially created population which one will be better. So which one will be better will be given a chance to mutate, so that in its near periphery we try for the new set of solutions. So in this way, at random we cover some amount of space and try to find out an optimal solution within that. Okay, so that affinity function, as I told you, has to be developed for determining the strength of a solution, and based on that we actually keep on searching. Okay, so based on the affinity function values, some receptors with high affinity values are selected from R. So within this set of receptors R, some of these values, based on this affinity function values, some of them are selected, and those selected affinity function values are known as RH. Okay, the set of RH is expanded by applying clonal. So once we get a acceptable value, then we clone this. We make clones for R with certain mutations, and we keep on searching. Or searching means we try to find out the better values of objective functions, or we try to find out better and better solutions. Okay, so a collection of receptors Rm are generated. So while at the same time, the set of receptors. Okay, so over a period of time, this is a collection of generated by applying appropriate mutation operations over RH. So RH is a set of selected solutions and cloned solutions from R set of initial populations. Then from this RH, we get Rm. We derive Rm by applying proper mutation operations. I'm just writing in a theoretic, formal notation. So from this set of RH, we obtain the Rm. Okay, what is RH? Just to clear, we initially take a set of initial population within the search space with certain objective function values. Now within that, RH gives you the set of better solutions. How do we know which is better? We define an affinity function which is specific to a particular problem, and then we get RH, and then we clone. We make a number of clones for RH. We mutate them, and then from there we get Rm. So we basically have a set of R initial population. From there we get a set of acceptable solutions which we clone, and from there we mutate and gets a set of mutated solutions. Okay, so this R, RH, Rm based on their observation values. So finally the best set. So from here, from all these sets, such operations are done, and we find out the best solutions. Okay, so this is carried out in different iterations of cloning and mutating. So these are carried out. I'll go back to the PPT, and then we'll see. So clonal selection algorithm. So the essential steps are, as I already have told you, how to obtain R, Rm, and all. So now this gives a prominent example pertaining to the machine cell formation problem. Okay, so these are to do this mapping. So they are encoded. Okay, the machine cell and part family are encoded. So this shows an example of a machine cell being encoded. Okay, so machine cell has to belong to exactly one cell. That is okay. This is one of the hard constraints. I wrote the equations previously, and each part belongs to exactly one part family. Another constraint. So machine cells are encoded as a vector. So one-dimensional matrix, namely, let us say machine vector 1j, which signifies that the jth machine belongs to the kth cell. So it should look like this. So for cell 1, okay, so this will go to cell 1, this will go to cell 1, this will go to cell 1. So these are the, so accordingly you can find, it's a one-dimensional matrix. So 2, 6, and 10. Similarly, portions which will go to machine 2 are element 1, 2, 3. So 1, 3, 4, 5, 6 is not there. 7 is there. 8 is there. So 1, 3, 5, 7, 8. 1, 2, 3, 4, 5. See, all of these are 2s. So like that we develop this. So these 5 elements are part of cell 2. Okay, so here it is showing the encoding of different machines to machine cells. So the range of values in this case is, the range is 1, 2, and 3 only. Sorry, 1, 2, and 3. Okay, so 3 cells. So cell C1 will have what machines that we can find from these entries. So those machines will go to cell 1. Which machines? So these are like the number index values. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 machines are there. So this, the division of machines to machine cells are being encoded as a vector, a single vector. So 3 cells, those 3 cells are, I mean, their components can be derived. Similarly, for the parts also, exactly it can be done exactly using the same logic. Okay, so this is how they are encoded. Now we are discussing the cell formation problem per se. So the essential steps, the first step, essential step is to define the receptors and all. So that we will do based on this structure. So it has not mentioned somewhere. We missed the initial population. So I mean parameter initialization. One very essential important step in the cell formation problem while mapping the what we are discussing here is how to map the machine cell formation problem as a clonal selection algorithm. So the first and most important point is to initialize the parameters. What are the parameters? The termination criteria. Okay, so after how many iterations, 100, 1000, whatever. So that value has to be fixed. Also the various parameters such as the sizes of these different receptor cells, R, RH, RM, and so forth. So how they have to be initialized. Okay, so for this work in this paper, we have of course used 50 as the number of iterations. And the choice of parameters such as the mutation probability, the expected distribution of random numbers, so what should be their range, and also these all have to be discussed. Then the encodings have to be done both for the machine cells and as well as for the part families. After this machine cells and part families are done, I mean encoded, we define the affinity function. Okay, so in this case the affinity function is defined as 1 plus, it doesn't work, total ICM. ICMT means the total number of intercell movements to raised to the power of V number of voids and total number of exceptional elements. Okay, so that's it. We have used it, I mean, based on hit and tell and based on ideas from how different people have used. So all these parameters have to be defined. And then what we do is that this diagram shows the machine cell and part family encodings for a very specific 10 cross 10 case. So 10 machines, 10 cross 10 machine parts. So 10 machines, 10 machine parts or 10 parts. So divided into 3, as you can see here, 3 different machine cells. So 3. Machine cell 1, so this is cell 1, this is C2, this is C3, right? So the different machines and parts are divided and accordingly. So we have done it in bits and pieces. This shows a concrete example for a 10 cross 10 machine, 10 cross 10 machine part binary incidence matrix. So that means 10 machines and 10 parts. Okay. However, so I'll just start concluding this session about the results. Before I do that, I'll just brief on this, the mutation functions. We also used mutation. So the mutation function, already the vector notation for this machine and part binary cells has been discussed. So this shows a mutation between position 1 and position 4. Okay, so this is swap 1 4. It's not right. It's looking like 9. Swap 1 4. So what we are doing, we are swapping the elements at index location 1 and 4. So see, after swapping, So this comes here, 3 comes here, and 2 goes here. The remaining, see, all the elements, they are all same. 1 remains 1, 2 remains 2, 2 remains 2, 1 remains 1, 2 remains 2, 2 remains 2, 3 remains 3, 1 remains 1. So this shows a swap function. So similarly, we generate, like within this range of 10, we generate random positions and then swap it and then try to find out which mutated version gives better solution for this affinity function. Based on the objective function, we find out, as I told you, which gives a better lower minimal affinity function value. So now this shows the hybrid clonal selection algorithm. So here we have done something. So we have used, why it is called hybrid, because on top of this clonal selection algorithm, we have used genetic algorithm to generate the initial populations. Okay, so that is done in such a manner. Of course, this comes by hit and trial with some expertise. We have found out that this reduces the possibility, this by hybridizing clonal selection where with GA. So what we are using is GA plus CSA. GA is used for generating the initial populations intelligently, such that actually we will never they will always generate only feasible solutions. Okay, so that means all the hard constraints are checked right away at the initial population generation step itself. So we don't have to recheck for it once we do the clones and mutations. Okay, so this gave us quite improved, drastically improved performances. So those details are also given. I can share these slides with you. So the part assignment heuristic. So then that's all about it. So based on this, we actually found out marked improvement. So this, as you know, this cell formation problem, they have been studied by different people. A large set of researchers, volume of researchers have been doing it. So however, our work was unique because when we did it in 2016, most of the other people, researchers, they had done it for 18, 20, 25, 30 test instances. So our proposed, GA hybridized clonal selection algorithm outperformed that. Not only that, gave us better performance overall, but then one of the main contributions of the paper is that in a single paper we had tested as many as 52 test instances. That means 52 different incidence matrices for different production problems. So and it performed well across practically all the 52. So for some of these subset of these 52 test instances, we had obtained 10%, 15% improved results in terms of, we used group efficacy, of course. So in terms of group efficacy, we obtained 10 to 15 times, 20 times, 10 to 15% or up to 20% in some cases improved performances, right? So however, it's not that we could improve all. For some small, particularly for small sized test instances where the number of machines and cell parts were less and optimal solutions were found, but our solution could actually match those optimal results. Okay, so it found them. And we compared it with some other meta heuristics which were used. Some people actually used the original CSA problem, somebody used the ant colony optimization problem, somebody used PSO, and so forth. So we compared everything, and then we also did some statistical analysis, because unless we do a statistical analysis, the results that we obtained does not have much of credibility. Okay, so like it might so happen that we already, as I told you previously, that an empirical comparison of our results given by the hybrid CSA, so that outperforms others, whatever I'm claiming, 10 to 15% for most on an average, and even to 20% in some 1 or 2 test instances, for larger test instances, of course. So this, however, this cannot conclusively assert that our method is superior to or good, at least comparative to other results. Okay, because it might happen, because we have used random processes for generating the swap functions. We have randomly used random functions to use the initial population. So that might be the case. So thus to validate the credibility of the obtained results. So the statistical tests on the results are very important. Okay, so this also I came to know across this. I never knew that something like that existed, statistical test for evolution algorithm. Also a part of my learning experience. So we used two particular statistical tests. One is called the Wilcoxon rank sum test, and also the Z test. There are many others, the student P test and T tests and all. So where basically we analyze the solution with a set of alternative null hypothesis and null hypothesis. We find out their mean, medians, and then compare. Okay, so we'll not go into the details, but even after doing this statistical analysis, we found that our tests were basically repeatable. So it gave us stable responses. So when we repeat the test with different initial population, it's not that our performance was drastically varying. Very minor variations were there. Before I end, I will also highlight some of the future works which we can do. So in all our works, what we did was that the ordering of parts, so that we actually ignored. So what we are saying is that in the different part matrices examples we told. So just I can go back and explain to you so that you get a flavor of what we are talking about. In this optimum, in this solution here, okay, or let us say here. So this says that in order to get obtain part one, we need assistance from machine 1, we need assistance from machine 3, we need assistance from machine 5. However, for all our solutions, we have completely ignored if there were any sequence which were required, like machine 3 first, then machine 1, then machine 5. It's not only us, practically speaking, all the literature, everybody has done it because it's too complicated a problem actually to formulate and then solve. So this was not possible for any real sized like 15 machines and 30 parts. So any real size problem, this becomes too complicated. However, computing capabilities are being bolstered every day. They are becoming stronger and stronger. So it is possible to solve. So that can be tried. I don't find anybody doing that. I have not find. For any real life test instances, for demonstration purposes with very small 3-4 machines and 5-6-10 different parts. Such problems where dependencies are taken care of, which machine has to be used first, then optimize the different part families with the cells. That has been done only for very small test instances. So this can be one of the works which somebody can take up in future. So in that sense, we have also taken that all test instances are also static. So in production cases, that is ideally not the case. The test instances can also evolve over a period of time. The requirements might change. So that also we have not taken into account, as is the case with all other these things, literatures which are existing. Okay. So we have actually in mind how to apply actually linear algebra based some pre-processing techniques for performance improvements, and also some graph partitioning based algorithms. So anyway, this has got nothing to do with we should not say nothing to do with, but the problems are there. The mathematical treatment is what we are talking of. So that's all about it. I think we can have questions for a few minutes. I actually wanted to complete by 11:30, 11:40, but I got delayed because of that network problem at the beginning. I have a meeting also at 12 o'clock. So if there are any questions, any discussions, that we can do it right now.
Dear sir and madam, now the platform is open for open discussion. If anybody want to discuss or want to put any questions or inquiry, you can able to put in the chat box, or directly you can contact with the sir. No problem at all. Directly you can talk with the sir.
Yeah, that would be good. So even in case of like any long term, if you want to do, I'm showing my email IDs here. Yes. So that you can, if somebody is interested, because right now I don't have any scholar who is currently, I mean, actively pursuing these two solutions, this graph partitioning based solution and the future works which I told you. So these are there in my mind. So you can contact. Just for that, I'm displaying my email ID. Any questions in the chat box? So if there is something in the chat box, you please let me know, because I'm keeping my screen fixed on this
No problem,
slide.
no problem. You can put it on the chat box. Actually, today I'm getting the maximum persons are getting the network issues, sir.
Is it? I don't know. I came to office just so that I don't have any network issues.
No,
It's a LAN connection. I don't know how it got
yeah,
disconnected.
because maximum people said they're not. They are in the sometimes during this COVID period they are not reported to
No,
the.
that is understandable. Yeah.
For that reason, they've requested, sir, we are not getting this one like that. They are personally.
No, this happens, sir. Even expecting questions is also difficult, because at least from my side, I can say, as I took this class, had I taken this session on a board and a blackboard, then I would have got a different feeling, because it was easy for me to see whether the students are following, and they could have stopped me at any point in time. So that experience anyway is not there. Yeah.
Only one thing here you will tell, sir, it's a good one, but because you are doing the so much coding program and for that one, sir, what will be the benefit if you will do the work here? Is there any industrial requirement based upon this?
So right at the beginning, I told you one statutory warning. The statutory warning is that my discussion on cell formation problem and this production cellular manufacturing, it's called technically. So cellular manufacturing,
Mechanically,
yeah,
cellular
huh.
manufacturing plays a vital role, because there are
So many are there. So
many
details,
machines.
applications and all I don't know, but I can give you a layman's example. Like suppose you have a set of 5 machines of different purposes. So those 5 machines, using those, you are producing different products, like maybe different screws or bolts or something. So then how to optimize them the differences are there, most important. If all the products are of the same type, if varieties are not there, then it becomes a simple optimal assembly line is sufficient to address it. But when variations of different times, different products, then dependencies are there. So in that time, under such a situation, the setup time, like you have to move some parts from this machine to that machine, those are wasted time, because while you are moving, both the machines are waiting. At the same time, the parts also will be the parts are also actually traveling, so that has to be minimized.
Yes, sir. Yes,
Okay.
yes, sir.
So in a real production environment, the only challenge which remains is that to map that real production environment to these equations. We have the codes, we can get the solution, and then before we start such a divergent production problem, just set up accordingly, so that these intercell movements and voids can be avoided as much as possible.
Yes. Thank you, sir. Anybody?
Okay, I think it's good. I also have a meeting. I think it's okay.
Okay, sir. Thank you so much, sir, for your kind presence here.
You're always welcome.
Thank you, sir. You're always smiling, smile face, and your talks are
No, but at the beginning, I'm telling you, had it been on IoT or something, I would have been giving you examples, because I work on that area. This is slightly different.
As you told, sir, again, I'm telling you, in this open platform, I have going to start another FDP2. FDP2, most tentative time is 24th to 26th, and now I started the contact with the speakers. Right, sir, and we are in the planning process.
Yeah, that will be more interactive, I guess.
Yes. And there also regarding, because I know that IoT based means you are, sir, so many people. You can say genius what you have done it.
Yes, but I have done some work.
No, sir. Sir, you always telling that you are doing the small thing, but I know that how much achievement you got and in which arena you are and how you are helping to the people. Right, sir. So there also I invite you right. In the you can say that from the beginning only, I am giving you on a request here, sir, regarding that IoT. You will give it one slot there in that FDP.
Yeah. Sure, with pleasure. No issue. Hope the participants have benefited. Thank you very much. With your permission, I'll leave, sir. I have a meeting. So
Yes, sure,
in
sir.
10 minutes
Thank you.
of time.
Thank you very much, sir. I will talk
Thank
to you
you.
after the in the evening, sir. No
Sure,
problem.
I'll
Thank
call
you.
you back.
Thank you. Thank you, sir.
Thank you.
So, dear sir and professor, I cannot tell you the participant because as I'm conducting, then in one side I can able to tell to others participant, no, all are we are colleagues. Some are my seniors, some are my juniors. Okay, so whatever me with my heartful respect to all of you. Is a nice program is going on, and I'm getting the more feedback from others outside also requested to be joined. But thing is that some peoples are not joining. That is the thing, and some are requesting to join in this one. To give allow us for a registration. Actually, this program is already 2 to 3 days of over, and already we are registered. So for in the meanwhile, we cannot allow any other persons to entertain in this time, but they can able to get the chance for the second FDP. We are going to plan very shortly, and it will going to start from 24th or 26th. The date is not till now; it is fixed, but it is going to be start soon. There also those person who not join, they can able to join your colleagues, you can report it, but that at that moment we are thinking that the seat is not till now, it is final, how many candidate we will take it. Number one. Number two, sir, we are giving the feedback link to the registered mail ID. Please fill it, because it is a sufficient time I am giving, because somebody's are there, some network issues are there. Okay, so I am helping from my end to run this program with your only cooperations, because all of us, I'm not telling that I am doing here a party or festival and then somebody will get invited for that one. No, it is required for all of us. It is required to all of us, and this is one platform we are getting by opportunity from the government side to, you can say that, encourage our knowledge, or to, you can say that, update our knowledge, to upgrade our skills, to upgrade our technology with the technology only. Here so many persons are good cooperating also, and I will thanks to each and every participant that who are involved here, and those who are missing that one, that YouTube channels are there. For that reason, live session we have done it. You can directly go with that one. Directly you will link on that live session. You can able to see every time. This is on the social networking system. Okay, so at any moment you can see that one. It is I've seen that yesterday. It is operating well and good. And each and every day you are getting the link. On the same link you can directly see, or you can go with this channel. Then you can directly see that one. And regarding the recording, and the recording very soon, within 1 or 2 days, I will put it in the Google Drive. I will give the link. You can able to download that one. Due to certain only problems, I cannot able to do at a moment, because I'm single handling all the things. So I will give. I'm trying it today evening or tomorrow evening. Right, all the links, all the recording I will put there, and I will give a link to all the registered mail ID. You can able to download from your end as per your free time. Okay, sir. So same thing I'm telling you, sir. Again, very soon, within few minutes, I'm sharing your feedback link to your register mail. So kindly fill it. If any suggestions, sir, you can want to give me, then you can directly talk with me. No problem at all. Right? I'm doing. I want to help you for everybody in a smooth manner. How we will conduct, how we will get more. You can say that term and technology. You can say that in one day, nobody can able to learn and implement it. But slowly, it when you will go acquaint with these terms, technologies, then you will start practicing, because so many platforms are there, so many softwares are there, so many persons are there to cooperate us. Okay, so again, one thing is that I'm telling you, before one session I put it for the particularly for all everybody, one robot analyzer, that is the software freely available. You will just download that one. On that practical sessions I will show you how to operate that one, and this through this one we can able to do the BTech program projects also. Right, robo analyzer, particular one small software, you can it is a freely available. You can able to download that one, and you will upload on your system. Only the skill sir will tell to us how to operate it, and from one small project we can able to do through that robo analyzer softwares. Okay, thank you all. I will send it the registration link to all of you through your registered mail. And afternoon session you will again we will join. Thank you all. Shravan sir.
Okay, sir. Thank you.
Yeah,
Afternoon
yes,
4.
yes,
Same
sir.
time 4 o'clock.
Same time,
Afternoon.
4 o'clock, all of you.
Sir, one small suggestion.
Sure, sir. Sir.
Can you make that afternoon session 3 to 3:30, if it's
The
possible?
afternoon time, na sir.
Yes, sir. Because
Yeah, I know it,
evening
sir. No,
it
I
finished
know,
6 to
I
6:30.
know it, sir.
We go to
Actually,
home.
yeah, no, I know it, sir. Actually, what is the problem? Those speakers to whom I contacted, they have a free slot on that time only. That
Oh,
is the bigger problem for this time. Else,
okay, sir.
I thought that I will go with the 10 to 12 and again 2 to 4.
Ah,
Okay. So,
if it's possible,
yes.
means just a suggestion,
No,
request.
I got it, sir. Because the maximum professor, they are also trying to, because this
Yes,
see,
sir.
sir,
Yes,
with
sir.
their busy schedules, sir. What much, because if you will go with them, then only we can able to know the real on the actual problem what is going on nowadays. Because these professors are working with the various industries, associated with the various industry, and they're solving the industrial problems. So
Oh,
these kind of problems, when we will get it now, that will be the real feed, that is the real, we are hungry for that one only. These are the real thing we want to capture, and we will start it. And these professors to whom I just connected with this FDP program, sir, each professor are a familiar, and they will help to each and every person. So if you personally also interact with them, they are ready to help you, and you will can send a drop a message to their, either to their mail or their contact number. They will help. They are you can say that help on their level best. Because I personally I have taken the help from them, and that is the greatest persons. Because once the program over and every bill will go, then that is not. This is the platform where we can interlink to each other. We have a good community. We have to generate a communication system between each other. We will build a good relation. This is the platform, and we can able to share our experience. We can share our work, and wherever we are facing the difficulty in our work, we can get the same other person from the same field.
clear
Okay,
organ,
so
madam.
this is the only one thing. This is the only one platform where we can able to build our relation for the research work and personality also. Okay, sir.
Okay, sir.
Okay. Thank you, sir.
Okay, thank you. Thank you.
Thank you very much. Sir, I will send the feedback to, you can say that to your registered mail ID. So all of us, we will just again will join at 4 o'clock. Thank you to all.